Which question is this?
Okay, question 8.
Let A be
Let
1, 1, 1.
A be
A 3 by 3 matrix 1, 1, 1. 3 ones. 0, 1, 1. 0, 0, 1.
okay.
Use Cayley Hamilton theorem to compute the inverse of the matrix A. Kramer. Cayley Hamilton. Cayley Hamilton theorem.
To compute the inverse,
The
right?
inverse of A. Have we done this in our class?
Yes.
No.
It's very simple. Are we ready? What's Cayley Hamilton's theorem? We've done it before.
Yeah, we have CA.
Somebody wants to get A. Somebody wants to get A. Hey, I see you. Oh! Solution.
Which is referring to?
It's
me.
It's now. I'm telling you, who is this person? With what kind of shoulder is that? So, Cayley Hamilton's theorem says that the characteristic polynomial of A, substituting A, is 0. That's it.
So how can that be?
Obviously, the determinant of this is not 0. Why? It's an upper triangular matrix.
Yes. So
So the determinant is the product of the diagonal. 1, 1, 1. So the determinant is 1.
Yes.
So I'm sure that A inverse exists.
Yes.
You can write it. Obviously, the determinant of A is equal to 1.
They will try copy.
No. You can write in bracket 3D. You can say what? Upper triangular matrix.
Since we have A is an upper triangular matrix. That's my language.
Okay. So therefore, what does this mean? This implies that A inverse exists, right?
Yes.
The next is to get the characteristics equation. To get the characteristic equation, you need to find the eigenvalues in quote, as if you are finding, but you will not find it. You have A minus lambda I. The determinant of that is equal to 0. So this is actually 1 minus lambda, 1 minus lambda, 1 minus lambda. Every other thing remains the same. 1, 1, 1. 0, 0, 0. This is still an upper triangular matrix.
Yes.
So that means that the determinant of this is simply 1 minus lambda cubed is equal to 0. This is the characteristic equation. But if I want the characteristic polynomial, I'm not supposed to leave it like this. I should open it up. Okay? So opening it up, I have 1 minus lambda, 1 minus lambda, 1 minus lambda is equal to 0. What does this mean? It means that 1 minus 2 lambda
Plus lambda squared.
plus lambda squared times 1 minus lambda is equal to 0. But what does this mean? It means that 1 minus lambda minus 2 lambda plus 2 lambda squared plus lambda squared minus lambda cubed is equal to 0. We have 1 minus 3 lambda plus 3 lambda squared minus lambda cubed is equal to 0.
Yes.
So ordinarily, without thinking at the back of my head, I know that this is it. But I just opened it up
Using binomial
because of us.
1, 2, 3, 1.
So
You're right, sir.
So what do we have? We have that this is the characteristic equation. So we have CA lambda is equals to 1 minus 3 lambda plus 3 lambda squared minus lambda cubed is equal to 0. Right?
Okay, yeah.
So what does this mean? If I substitute A, that means that CAA is equal to I minus 3A plus 3A squared minus a cube is equal to 0. I know a inverse exists. So if I multiply that with a inverse, I have a inverse. I'm multiplying a inverse from the left hand side on both sides. I have a inverse I minus 3a plus 3a squared minus a cubed is equal to a inverse times 0. This is 0 matrix, not just 0, okay? So I have a inverse minus 3i plus 3a, right?
Yes.
Minus a squared is equal to 0. Make a inverse the subject of formula. I have a inverse is equal to a squared minus 3a
plus a
plus
squared.
3i. I took this to the side, minus, it became plus.
It's okay.
So you can take your time and substitute. You get a squared from this, get 3a, get 3i, and get your answer. Yeah, done. So that's, I would like you to post your answer in the comment. Even if you get it here, go and comment on my channel, post the answer. Thank you. Okay, number 9. Let a
Equal to
be equal to
minus 1, 2,
minus 1, 2,
4.
4.
Then 0, 0, 5. Then 0, 0, 1.
Okay.
This is also a part triangular.
Okay. So
explain why a to power 1001 is equal to a. Is a to power 1000 an identity matrix? They say explain why a to power 1001 is equal to a. Then the next is a raised to power 1000 an identity matrix? How do you solve a to power?
when I saw this question, I was also afraid.
Yeah.
There's nothing to fear.
Okay.
So the polynomial we have here is x with respect to x
Okay.
is x raised to power 1001.
Okay.
Okay. But we need the polynomial here, the characteristics polynomial. So we need to find a minus lambda I.
Okay.
Right? But a minus lambda, we need it to be equal to 0. A minus lambda I is minus 1 minus lambda, 1 minus lambda, right?
Yes.
0, 0, 0, right?
Yes.
2, 4, 5.
Yes.
Okay. So this is another triangular matrix. So the determinant is obviously minus 1 minus lambda times minus lambda times 1 minus lambda.
Okay.
Right?
Okay.
This is equal to 0. But this is, if I multiply with minus, I have lambda
Plus
1 minus lambda, sorry, 1 plus lambda, 1 minus lambda is equal to 0. So here we can see that lambda is equal to 0, lambda is equal to 1, lambda is equal to minus. If you observe, the degree of this is what? Is 3.
yes.
The degree of this polynomial is 3, right?
Yes.
And the polynomial x is equal to the characteristic equation of a, which is this is the characteristic equation,
Yes.
times some q of x. This polynomial of x is this, plus some remainder. And then the remainder of x has a degree. The degree of this minus 1. So it has degree 3 minus 1. It's a polynomial of degree 2.
Yes.
So we can let r of x be equal to beta naught plus beta 1 times x plus beta 2 times x squared. We can now substitute each of these roots into this, okay? We have that p of x is equal, because the characteristic equation will give you 0. So p of x is equal to r of x, okay? The characteristic equation, from what we have seen, this is 0.
Yes.
If I multiply the characteristic equation with anything, it will still give me 0.
Yes.
It plus this. So that means that this remainder is equal to this.
Yes.
So P of x is equal to R of x. Okay?
Okay.
So-
For the lambdas that will make
Yes. So we are now going to take x to be 0 first. For
Okay.
x is equal to 0.
Mhm.
P of x will be 0 raised to power 1000, which is 0, right?
Yes.
P of x is equal to 0. Is equal to R of x. R of x is just beta naught, is it not? Because every other thing is 0.
Yeah.
So we have gotten beta naught. Now for lambda, for x is equal to 1.
Yes.
What do you have? You have that P of x is 1 raised to power 1000
Yes, which is 1.
is equals to 1. And this is equals to R of x, which is beta naught plus beta 1 plus beta 2. Right? That's all.
Yeah.
But we know that beta naught is 0.
Yes.
So what does this mean? It means that beta 1 plus beta 2 is exactly 1.
Yes.
So I can call this equation 1.
Okay. Right.
Let me call this down.
Yeah.
So now for
X
is
for
equal to
lambda.
minus 1.
Mhm.
That's this one, this part here.
Mhm.
What do we have? We have minus 1 raised to power 1001. It's still minus 1 because it's odd.
Yes.
So P of x is equal to minus 1 raised to power 1001, which is equal to minus 1. And then R of x from here, I'm substituting. I have beta naught minus beta 1 plus beta 2.
Mhm.
So I know this is 0.
Yeah.
So what do I have? I have that beta 2 minus beta 1 is equal to minus 1. So call this equation 2. Okay? So
we have
equation 1 and 2 is simply beta 1 plus beta 2 is equal to 1. And then minus beta 1 plus beta 2 is equal to minus 1. That's what we have here. I just made minus beta 1 to come first. So if I add these two, what do I have? I have 2 beta 2 is equals to 0.
So delta 2 is always 0.
Good. And obviously beta 2 is
Beta 1
0.
will be
Beta 1 will be 1.
Which is
I just
8.
substituted 0 here and I have beta 1 is 1. If you do the same thing, you still have beta 1 is
So
1.
delta 1 is equal to 8.
So this implies that R of x is equals to 0 plus 1x plus 0x squared. So that means that Rx is equal to x.
Yes.
But you know that PA is equals to RA, is it not?
Yes.
But PA is A raised to power 1001.
Yes.
It's equals to, what is RA?
X.
X.
Which is
It's
equal to
I don't know.
A.
Explain why this is equals to this. This is where we have A raised to power 1000. I just need to change this polynomial of x to be 1000, okay? Now I know that that's 1000. It's going to affect everything from down here. That's my Rx. I'm going to have a new Rx. Okay? My Rx is still of this form, raised to power 2. So how do I get my new Rx? P of x when x is 0 is what? 0 raised to power 1000 is still 0. Is equals to R of x. This is still going to be 0, 0. So I have beta naught, which is R of 0. Okay? So I can see that beta naught is equal to 0. For x is equal to 1. We have P of 1 is 1 raised to power 1000.
Which is 1.
It's still 1, right?
Yes. So delta naught.
And this is going to give me, I'm going to put 1 everywhere here. I have beta naught plus beta 1 plus beta 2. But I know that this is 0 from up here. So this is equals to R of 1. Okay. So this implies that beta 1 plus beta 2
is equal to 1.
Is equal to 1.
So the same thing with the third one.
Yes. Now, so P of minus 1
is
equals to minus 1 raised to power 1000,
which is 1.
Which is still 1. which is going to give me beta,
You say
plus,
answer now. Delta 1 plus delta 2 is equal to
it's now minus. It's now minus.
fine.
So I'm putting minus here. I have minus beta 1 plus minus 1 raised to power 2 is now 1. So plus beta 1, beta 2, sorry. So this is equal to this. So that means that this is 0. Beta naught is 0. So this means that minus beta 1 plus beta 2 is 1. So let's write that here. If I add, I have that beta 2
is equal to 1.
is equal to 2.
So delta 2 is 1.
2 beta 2 is equal to 2. Beta 2 is equal to 1. And if beta 2 is 1, then this must be 0. And beta 1 is equal to 0. Our new Rx will give me beta naught, which is 0, plus beta 1x, which is still 0, plus beta 2x, which is this. P of A is equal to R of A, right? This is A raised to power 1000 is equal to A raised to power 2.
Which is equal to A.
But how are we sure that it's equal to A?
Okay, we are not sure.
What is A squared? We need to compute A squared. A is equal to, we are not sure. They said is minus 1. A squared is equal to minus 1, 2, 4. I'm copying from here. 0, 5, 0, 0, 1 times itself again. This will give me this times this 1. All this will give me 0. This times this minus 2. So you are saying that it's not going to give me identity.
It's not going to be.
Thank you. Which is not equal to the identity matrix. Therefore, A raised to power 1000 is not equal to the identity matrix. So is that my answer is no. A raised to power 1000 is not an identity matrix. If you look at this, that A raised to power 1001 is equal to A. Somebody would have been tempted to do this. Everybody look up. Don't do it.
1000 times.
You can be tempted to say, A raised to power 1000 is A raised to power 1001 is equals to A times A raised to power 1000. But we know that this is A, right?
Yes.
If you look up, A is not invertible.
Okay.
You may be tempted to multiply by A inverse, but A inverse does not exist.
Okay.
If you multiply by A inverse, you have A inverse A raised to power 1000 is equals to A inverse A. So you will say A raised to power 1000 is equal to I. But this is not true because A inverse does not exist. So you cannot do it. The easiest way to see that A inverse does not exist, you can see that A is an upper triangular matrix.
Yes.
So the multiply diagonal, you have minus 1 times 0 times 1, you have 0. So A inverse does not exist. So don't be tempted to do this. This is totally wrong. Don't do it.
So there.
So is the correct question, not the one we did during time?
So by the time, do
This
you
is
need to
correct
go?
solution.
Do you need to go?
This one is the
far?
correct solution.
Do you need to do the square?
Yes.
Because if you know from there to that one, there is no identity.
And the square is not identity matrix.
From the fact that this is uninvertible, no?
No, you cannot say that. You cannot know immediately.
Okay.
You cannot know immediately.
That's nothing.
You need to multiply.
Let me see what it's doing. Let me see what it's doing.
I'm just hoping. So I'm looking for shortcut under example.
I understand. But you can't conclude like that. You need to get what A squared is.
You always don't agree with me.
Number 10, so that I can go home. So. Don't mind me.
Let me calculate.
Let me finish my video.
Oh, thank you.
Okay, number 10.
Thank you for watching. Please subscribe to my channel.
Thank you.
See you in the next video. Thank you.
The last question, 10.
So here we have a matrix, this. I was supposed to compute its minimal polynomial and deduce whether it is diagonalizable. If it is not diagonalizable, then we'll find its Jordan normal form. And
The matrix.
the invertible matrix P such that AP is equal to PG. Okay, solution. To find the minimal polynomial, you need to find the characteristic equation first.
Yes.
After finding the characteristic equation, you will now find the smallest polynomial such that multiply the polynomial will give you, the product or whatever, will give you 0.
Okay.
So let's find the characteristic equation. And determinant of A minus lambda I is equal to 0 implies that determinant of 2 minus lambda, here will be 0, 0, 1, 0, 2 minus lambda, 1, 0, 2 minus lambda. So this is an upper triangular matrix, right?
Yes.
So we can see that the determinant will give me what? 2 minus lambda cube is equal to 0. Okay?
Yes.
So
we need to expand because
when this is the characteristic.
To expand.
This is 2 minus lambda cube because the minimal polynomial, you see that the root is just 2 here.
Yes.
It's only one root.
Yes.
So we can have the minimal polynomial to either be 2 minus lambda or 2 minus lambda squared or 2 minus lambda cube. You can check it, I've checked it myself. You can check that CAA, the characteristic polynomial with respect to A will give you 2i minus a cube. So you can check that 2i minus a and 2i minus a all squared is not 0. They will never give you 0. You can check it. Take your time and check it.
Okay.
So since these two cannot give you 0, then you are left with 2i minus a cubed. And we already know that that's 0. So that's the minimal polynomial. So the minimal polynomial is 2i minus a all cubed. And you can say that this is just what? Lambda is 2 minus lambda all cubed. We found the minimal polynomial. We now want to deduce whether it's diagonalizable. If you observe, we have that the root of this equation from here is what? 2, 3 times. Right?
Yeah.
Since this root is not distinct, there is a theorem that says that if the roots are not distinct, then it's not diagonalizable. So simple, we say that A is not diagonalizable because the roots are not distinct. Okay. Now finally, if A is not diagonalizable, we find the general normal form. Obviously, A is in the general normal form. General normal form says that I'll get all the eigenvalues, which is 2, 3 times. I'll put it on the principal diagonal. It's a 3 by 3 matrix, so I'll put it 2, 2, 2. Then the leading diagonal above this principal diagonal, this next diagonal, everything on top of it should be 1, 1. Okay? Then every other place is 0.
Which is 4.
Which is exactly A. So I found the J. This is J. And this is exactly A. Is it not?
Yeah.
So the remaining thing is to find P. So let's find P. How do we find P? We know that lambda is equal to 3 times, have we? It's equal to 2 thrice. So we also know that A minus lambda I times a vector, say V1 or V, let's call it V first, is equal to 0. But A minus lambda I is this minus lambda I, so we have times V1, V2, V3. Is it not? I would have preferred X, Y, Z, but no problem. I don't need variables. What is lambda? Lambda is 2. So I can substitute here. 0, 0. So I can see that here is multiply this with this. I have V2 is equal to 0. Multiply this with this, I have V3 is equal to 0. But since this rule is 0, right? It's free. So the free variable is V1 because it doesn't have the solution yet. So V1 is equals to say alpha. So we have that V is equals to alpha 0, 0, which is alpha times 1, 0, 0. We have only one vector, that's the problem, we need more vectors. Okay? So what do I do to solve this problem? I simply say that A minus lambda I, let me call this V1, times V2 is equal to V1. V2 is what we are looking for. V1 is this that we already know. We can take it to just the side. Okay? So we have, this is, lambda is still 2. Okay? So I still have this vector, I still have everything except this side. I have V1, V2, V3. 1, 0, 0. So from here you can see that this time this is V2 is equal to 1. This time this is V3 is equal to 0, the second one. And we have a free rule. So V1 is say alpha. So what do we have? We have that the big vector V2 is equals to alpha 1, 0. I can't bring out alpha. Be careful. But what I can do is I have 0, 1, 0 plus alpha times 1, 0, 0. If I bring out alpha the way I did with this, it will affect this one. Do you understand?
Sorry.
So now, this is exactly V1, I don't need it. I'm going to take my V2 to be, I can take alpha to be 0, and take my V2 to be equal to 0, 1, 0. I will do the same thing which you can do. I'm going to use this as my V2. I will do A minus lambda I times V3, which is what I don't know, is equal to this V2 that I found here. And I'm going to get that V3 is equal to 0, 0, 1. You can check it yourself. So we have what V1 is, we have what V2 is, and we have what V3 is. So the matrix P is equal to, keep V1 as the first column, 1, 0, 0. Keep V2 as the second column, 0, 1, 0. Keep V3 as 0, 0, 1.
I wanted to ask.
We have that this is identity matrix. We have A times P is equal to A times I, right? Is equals to I times A.
Because J.
This is equal to P. A is still J, so PJ. And we have seen that that satisfies it. So we have found J, which is exactly A, and we have found P, which is the identity matrix, so that AP is equal to PJ. And we are done.
But instead of doing all these calculations, from that the Jordan number that we got the same to the A, can we just say that
P is identity matrix.
P is identity matrix?
No, it's easy to see, but it's not advisable to just say.
We lose marks.
Okay, that's the end of today's. Hey, that's the end of today's solving. Thank you for sticking with me till now. I'll see you next class. Bye. And finally, actually, this is the end of matrix theory for this exam preparation. This group study block. This is the end of matrix theory. The next course we'll be doing is advanced calculus. See you then. Bye.